So you have learned the three relationships between pressure and gas and temperature. We know that pressure and gas and temperature, pressure and volume and temperature. We know that pressure and volume vary indirectly, which means if you multiply the pressure of the volume and then you change one of those two on a gas, that the other will change in the opposite direction. So we know that P1 times V1 is equal to P2 times V2. All right. We know that pressure and temperature, so that first one's Boyle's law. This next one, we know that pressure, or let's do volume and temperature next, is Charles' law. And volume 1 and temperature, they vary directly. So if you change one, the other one is going to change in the same manner. So you double one and the other one will double. Okay? That is Charles' law. So here's Boyle, here's Charles. And then the third relationship is sometimes called Edmonton's or Gay-Lussac. But it's really a function of Charles' law. All right, so we can actually put those three together. And if we put them together, we get, see how cool this is. Probably won't be cool at all. Work. There we go. That sort of work. We can put them together and we get PV over T. This is called the combined gas law. And again, you plug in your variables and solve. Gas law problems are very simple. Now, the fourth piece that we talked about in the notes, we talked about pressure, volume, and temperature. The fourth piece was number of moles. And I used an example of if you're blowing up a balloon, more breath going into the balloon makes the balloon bigger. So that means volume and the number of particles are also directly changing. So I'm going to put N in down here. So P times V divided by N times T is equal to P2V2 divided by T2 times N2. Okay? Now, remember we introduced the idea of standard temperature and pressure. At standard temperature and pressure, 1 mole of a gas has a volume of 22.4 liters. So we can finally fill in that last blank on our mole map. Now I have to figure out where the mole map is. Let's see. Here we go. We're going to fill in that last bit. So, write volume of a gas in the upper left-hand corner. Okay, if you don't have this, get it out, pause, get it out, get ready to write. Okay? So we know that 1 mole has a volume of 22.4 liters. So if we know moles, we can multiply times 22.4 liters in 1 mole, and we'll get a volume. And if we know volume, we can divide by 22.4 liters for each mole, and we get moles. Okay? That is at STP. If it's not at STP, then you're going to have to do something different. But that is at STP, that relationship works. Okay, so let's say we're doing a lab with, you get so many grams of, do I not have the mole map, mole bridge? Guess not. So let's say we change grams to moles by dividing by molar mass. So we're doing a lab with magnesium ribbon and hydrochloric acid. Okay, so the first thing you would do is change, if we know that we have 10 grams of magnesium, you would change that to moles. Then you would go through your mole ratio. So if we're going from, let's say we're going to solve for gas, hydrogen gas. So this is going to be our unknown. And we'll use yellow for our known. So our ratio would be 1 mole of magnesium to 1 mole of hydrogen gas. So it's a 1-to-1 ratio. Now, that's going to produce moles of hydrogen gas. You can still calculate for grams by coming back down off the bridge and multiplying by molar mass. But what if they ask you how many liters that is? Well, you can then, looking at your mole map, if you know moles and you want to go from moles to volume, you multiply by 22.4. So on your mole bridge, you can add 22.4 liters per mole, and you'll get volume of a gas in liters. Okay. By the same token, if we know we have so many, we know we want to produce a volume of hydrogen, and we want to figure out how much magnesium to use, we could start with the volume of the gas in liters, and if to go to known amount, we divide by 22.4 liters per mole. Okay, so you can fill out those pieces in your book, or on your mole map, in your mole bridge. Okay, so here we have a gas and we've manipulated. We have the gas original settings, which is P1, V1, N1, T1, and we have a new set of parameters. What we want to do is create a standard which to compare it to. So I just told you at STP, 1 mole of gas has a volume of 22.4 liters. So I'm going to plug that in up here. And that's 1 mole of gas. What's STP? Well, for pressure, it means 1 atmosphere. And for volume, or for temperature, it means 273 Kelvin. Okay? So if we do the math, 22.4 times 1 divided by 273, we come up with 0.0821, and we get really funky units. Liters times atmospheres over moles times Kelvin. So now, if we have a gas, we don't have to manipulate that gas. We can just compare it to this. This is called the ideal gas law. And this value here is the ideal gas constant. Okay? So, the page in your book, and this number is, apparently doesn't have a number on it. I loaded it before I put numbers on it. But if you find this page in your book, here is R, what we just calculated. We know that PV over NT is equal to R. Well, we can arrange those numbers. This is P1, V1, N1, T1, and this would be P2, V2, N2, T2 at STP. We can rearrange that into this equation, and people tend to call this the Perv-Nernst equation. All right? Notice, volume has to be in liters. Pressure, for this case, for what we're going to use atmospheres. In College Chem, I just went through all the calculations on the new online stuff I have for the 4 kids getting credit, and every time we're given some kind of pressure measurement and we change it to atmospheres. And that is all back on the first page of the notes, the different kinds of atmospheres. Okay? You could also use kilopascals, but if you use a different kilopascals, you have to use a different constant. Here, I'll show you those constants. This is from notes that I gave to College Chem. All right. PV equals nRT. If we're using atmospheres, we use, let me erase this. If we're using atmospheres, this is our gas constant. But what if you're using kilopascals? Then you use 8.31. And what if you're using millimeters of mercury, which you learned about when you watched the barometer video, because you actually are measuring the height of the mercury column in millimeters, you would use 62.4. So you can use any of them. This is the one that I use, and this is the one I would always recommend. All right. Pressure, moles or Kelvin, you've got all that. Here we go. If we're using atmospheres, that's the R value use. If we're using, Teddy, don't whine. Here, this is what he's doing right now. He's lying here being pathetic. Yes, you're talking. You're talking to everybody. The kids are on here watching you, and you're lying there going, oh. You're pathetic. He wants to go for WALK or to the PARK. And it's a beautiful day, so maybe I'll do that later. Okay. So, these are, this is another formula you can use. And I'm going to go ahead and move through. I'm going to skip stoichiometry. We'll come back. Here are gas unit conversions on the packet of goodness. For gas unit conversions, 760 millimeters of mercury are equal to 1 atmosphere. 1 milliliter equals a cubic centimeter. Actually, I'm not too worried about you doing the gas unit conversions. You need to be able to do that, but most of you can do that, no problem. So let's go on to Boyle's practice. Boyle's law is P1V1 equals P2V2. So you just have to go through and solve. Now, this is a case you don't have to change milliliters to liters. All right, so here we have V1, P1, the pressure P2, and we're going to solve for V2. So you just plug it in. So there's V1, P1 equals P2, and solve for V2. All right, Charles' law, your V1 over T1 equals V2 over T2. So here we're given a volume 1 and a temperature 1. But what is wrong with that temperature? You have to convert it to Kelvin. And there's volume 2. So we set up 2.00 liters over 293 Kelvin is equal to 1.0 liter and some new temperature. It's going to be half of 293. I'll give you a hint. All right. Gay-Lussac is P1 over T1 equals P2 over T2. Same story with our temperature. Here's P1, here's T1 plus 273. And it says, what is the pressure at standard temperature? STP. What did we define standard temperature as? 273 Kelvin. So P1 is 0.370 atmospheres. T1 is 323 Kelvin is equal to P2 divided by 273 Kelvin. Yes, Ted, I hear you. And solve for P2. Combined gas law, you're just going to put them all together. P1V1 over T1 equals P2V2 over T2. Now, ideal gas law, we got to use Pfeffner. PV equals nRT. So let's go through and identify the first one. Here's N. I don't know if you're picking up the growling. There's volume. We're solving for pressure. Here's our temperature. So, pressure is what we're going to solve for. Volume is 20 equals N, 5. R value, 0.821 liter atmospheres over mole Kelvin. And T1 is 25 plus 273, 298. Okay? Yes, Ted. Hi. If you are more comfortable with the math, to rearrange this instead of adding it up, setting it up this way, you can do whatever you want to do. So that's how we use ideal gas law. I will come back and do another video on stoichiometry.